In Chapter 6, we are going to study the sections deal with programmable logic devices. So why do we need the programmable logic devices? The fact is that in an integrated circuit with a small size, so the footprint of a thumbnail, you can put thousands of gates there. But what we design is just use a small number of gates. So designing a small number of gates and then using the footprint of integrated circuits for millions of gates is a waste, and that's not very practical. So what we typically do is we put many modules and in those modules are small enough so that you can use for your own purpose, but those many modules are put together in a one IC. Those in smaller modules we allow that users can program those logics. That's the idea behind why we have programmable logic devices. So we have programmable logic devices so that we say it's a field programmable, means that ICs are manufactured but users can buy it and take it to their place, so there they can configure for their own logic. In addition to programmable, some devices are erasable and reprogrammable. So if you want to update the logic circuit or to correct the logic errors, you can just erase it and then program it again. So this is something ideal for course laboratories. Then programmable logic devices are sometimes used to prototype a design. So you design the logic and prototype it and test it if the logic is working correctly or not. And if the circuit is verified, then you can mass produce it. Actually, Intel Pentium is completely designed with a prototype before they put into mass production. So we have some technology characteristics based on whether you can reprogrammable or not. We have a permanent, which is just you program it once and then you cannot erase and reprogram again. Those are some technologies with mask programming or fuse or anti-fuse. So you can just imagine a blank CD. You can choose to just write it once and then you can no longer write it, so it's sort of a permanent. But reprogrammable is like a reader-writable CD. You can write the data and you can later erase and rewrite it. So we have something like that kind of characteristics called reprogrammable logic devices. So we have two kinds under reprogrammable devices. One is a volatile, which means if the chipset loses power, the program information is gone. But the non-volatile case is even if you lose power, the configuration remains unchanged. We have basically three kinds of programmable configurations. We have some other types which is more complex though, but basically we have three kinds. First one is called read-only memory or ROM. Another one is called a programmable array logic PAL, and another one is a programmable logic array PLA. Depending on which part of the device is programmable, we have a different technology. Basically, within the device, we have an array of AND gates followed by an array of OR gates. So basically, all those three types, you have an array of AND gates followed by an array of OR gates. So that's a basic configuration. So depending on which part is programmable, we have three types. Read-only memory has a fixed AND array, and then OR part is programmable. In the meanwhile, programmable array logic PAL is we have a programmable AND part, the fixed OR part. The last one, PLA, programmable logic array, you can program both AND parts and OR parts. So depending on which part you can program, depending on that, we have three types of configuration. So we can depict in a graph this way. So you have AND array, OR array, same structure. So depending on which side of the input you can program, you have a ROM, or it's called a programmable ROM. So we have a PROM, same thing as a ROM. And then if AND part is programmable, then we have a PAL. If both are programmable, we have a PLA. So read-only memory configuration, you have a fixed AND array and the programmable OR array. Basically, you have N inputs and M outputs, and internally it provides 2 to the N decoded minterms, which means you have N inputs, all possible combination of inputs. You can have minterms for each combination. So it's more like a truth table in that sense. So out of the truth table, you can directly configure ROM. So given Boolean expression, you configure or you construct a truth table. Out of the truth table, you can directly program ROM. So it's more like a memory device. So here is the idea. So you have a 3 input ABC and the 4 outputs labeled F0 through F3. So you have an AND array, which is nothing but a decoder. So you have 3 input and 8 output. So 3 by 8 decoder, which is AND array, it's a fixed. And then you have a OR gates. Here the diagram simply has a one line for each OR gate, but it's a shortened notation. But actually, this OR gates has as many as the number of outputs on the decoder. So this one single line actually represents 8 lines, one for each output of the decoder. And here X mark indicates that this OR gates are out of the 8 inputs from decoder output, that line D2 is connected, while others, if you don't have X there, those D0 input and the D3 input is not connected to the OR gate. So this OR gate, out of 8 inputs, only D2, D5, and D7 is connected. So here you can place the connection as you like. So here is a programmable part for the OR gates. So what it actually implements is, since we have a decoder, 3 inputs, if 3 input ABC is 0, 0, 0, then the D0 is 1, while all the other is 0. And then 0, 0, 1, and D1, and 0, 1, 0, D2, and then if we have a 1, 1, 1, D7 will be 1. So what F3 represents is a D2 or D3 or D7. Remember, this one single line is actually 8 lines. So D3, which has physically 8 inputs, but only 3 inputs are receiving signals. So F3 is all of D2 or D5 or D7. What is D2? D2 is when ABC is 0, 1, 0, which means A not, B, C not. So for F3, for D2 is when input is 1, 0, 1. The D5 is when input is 1, 0, 1. I'm sorry, D2 is 0, 1, 0. D5 is 1, 0, 1. The D7 is 1, 1, 1. So output F implements a function of those when those are 3 minterms. Similarly, F2 is OR of this minterm and that one. So this minterm is a D0 and that minterm is D7. So F2 is a D7 or D0. D7 is a 1, 1, 1. D0 is a 0, 0, 0. And the F1, we have two minterms, a D1 and a D4. So F1, we have a D4 and D1. So D4 means 1, 0, 0. D1 is a 0, 0, 1. And F0, we have three minterms, a D1, 5, 7. 1, 5, 7 are those. So using read-only memory, once the truth table is given for the function, so we can easily configure the OR part to implement the required function expression. Programmable array logic has a programmable AND array and then followed by a fixed OR gates. So it has a certain disadvantages and advantages over ROM. Let's see the configuration. Configurations like that. Something different you can notice is that as you have inputs were true form and the inverted form. So both forms are available, and then those are AND gate array. In the AND gate array, you can program inputs to the AND gates, but you have a fixed OR gates. The sum of the output can be fed back to the input of the AND gates, either in true form or complemented form. That's the basic configuration of a programmable array logic. Again, for each AND gate now, even if you have only one line drawn here, but actually the number of lines, the number of inputs to each AND gate is same as those in number of vertical lines. So you have 10 vertical lines. So you can imagine that each AND gate has 10 inputs. As you place X marker there, that line is connected for the input, and so on. You can interpret it that way. So what's the function implemented here? You can see this way. So as to output F1, F1 is a OR of those three AND product. So basically F1 could implement anything which is an OR of those three AND products. And each AND product could have up to 10 values. So what is got here is that first AND gate, we have only one X mark here, and this line is so this line is C inverted. So first AND gate of F1 is C and inverted. The second AND gate, you have two X marks. So first X mark is A inverted, and then second X mark is B inverted or complemented. So you have a product of AND of those two. The third AND gate is not being used. So function 1 is one of the four output of this PAL implements this logic. As to second output F2, which is again OR of three AND terms. The first AND term has three values. So this first line is A inverted. The second line is B in true form. And third line is C inverted. So first AND gate represent that value. The second AND gate, A in true form and C in true form. So it represents A and C, second AND gate. And third AND gate, A in true form and B in complemented form. So all of those three products. So function f2 represent that. And the function f3 is also all of three AND terms. So first AND term, A in true form, and then here is X mark, which is a D in true form. So A and D is the first AND gate. And second AND gate, what you have here is a B in true form and D in true form. And the third AND gate, X marked here. And what is this? F1 in true form. So F1 in true form. F1 is implementing this logic. So this F1 represents this logic. So eventually, if we rearrange that, this is what F3 implements. Similarly, you can figure out for F4. So this is a programmable logic, array logic. Compared to ROM, you have a programmable AND gates, and the OR gates are fixed. With the ROM, you had the fixed AND gate and the programmable OR gate. So that's the difference. And the third configuration is a PLA, Programmable Logic Array, where you have both parts are programmable, and or those both are programmable. So it has a certain advantages and disadvantages over PAL or ROM. Let's take a look at the structure using the example. So you have an array of AND gates here, and you have an array of OR gates here. Both inputs of the AND gates, the inputs of OR gates are programmable. That is a programmable logic array. Again, for inputs, you have a 3 input for the device and the 2 output for the device. One thing you can notice is the output part. The output part goes through exclusive OR gate. That's something different from the other two. Again, on input side, like a PAL, you have a both in true form and then complemented form. So both forms are available. Again, for the AND gate, you have only one single line shown here, but it represents multiple lines, as many as double the number of inputs. For each input, you have either true form or complemented form. So for 3 inputs, this AND gate represents 6 inputs. So you have 6 lines. You can choose to have those. So this AND gate also have 6 inputs and so on. For OR gate, you can see only one single line as an input, as a diagram. But again, you have inputs as many as the number of AND gates. So one single line here represents 4 inputs, 1 for each output. As you place X marker, that line is connected. If you don't put X mark, that line is not connected. So let's figure out what does this represent. For this AND gate, since those two are connected, so this line means A in true form, this line means B in true form. So output of the first AND gate represent A and B. Similarly, for AND gate 2, input is a B and C. And third AND gate, input is a A and C. So we label there for internal purpose. Now for number 4 AND gate, we have A in complemented form and B in complemented form. So that's the result of the AND gate. And now for the OR gate, so this first OR gate, the input is this guy and that guy. They are AB or A not B not. So that's the output of the OR gate. AB or A not B not. And for this OR gate, the input is AC or AB. So here, this line represents A, B, B, C, A, C. So 3 of those are connected for this OR gate. So this line represents again AB or BC or AC. Now for the exclusive OR, the other line of the exclusive OR is connected to 0. So if you have any variable X exclusive OR with the 0, the result is the same as the original variable. So for example, 0, 0 is a 0, 1, 0 is a 1. But if you have exclusive OR with the 1, then what you get is X complemented. For example, 0, 1 means 1, 1, 0, 1, 1 means 0. So that's the. So here for this exclusive OR, one input is connected to 0. Whatever comes in appears as is because of this property. So F1 is OR of AB, BC, and AC. In the meanwhile, the other exclusive OR gate, you have 1 connected. So whatever appears here is inverted on output F2. And what is provided here? Input is AB, this line, or A not, B not. So what is appearing on output F2 is invert of the whole thing. That's what appears on output 2. So here is the result. So F1 is directly ABC OR gate, but F2, this is input to the exclusive OR, and it is inverted. So if you rearrange that, what you actually implement is this function.